Your electronic devices could soon be 1,000 times faster thanks to a new quantum breakthrough. United States researchers used light to control a special material called 1T tantalum disulfide, making it switch instantly between blocking and allowing electricity to flow. This switching is the same core function that transistors perform in computer chips, but this method works at speeds close to the limits of physics. The process, called thermal quenching, uses rapid heating and cooling to change the material's state at practical temperatures and for long periods, unlike earlier attempts that required extreme cold and only worked for seconds. If developed further, this could replace traditional silicon chips, which are now reaching their physical limits after decades of use. Instead of linking separate conductive and insulating materials, future devices could use a single quantum material controlled by light to handle both roles much faster and more efficiently. While the technology is still in its early stages and not ready for consumer gadgets yet, it opens up a path to creating smaller, faster, and more powerful electronics. Quantum hardware could also enable entirely new kinds of technology beyond just faster devices. It could power ultra-secure communication networks, revolutionize data storage with higher capacities, and drive breakthroughs in artificial intelligence by handling complex calculations that overwhelm current processors. Industries like healthcare, energy, and transportation could benefit from more precise modeling and optimization. This is the most accurate clock ever made. It is so precise that it can measure a second to 19 decimal places, setting a new world record in timekeeping. Built by researchers at the National Institute of Standards and Technology, the clock works by tracking the tiny vibrations of a single aluminum ion paired with a magnesium ion, both cooled close to absolute zero. This pairing makes it easier to control the aluminum ion with laser light, giving the clock unmatched accuracy and stability. It is 41% more precise and 2.6 times more stable than any previous clock. And the time needed to gather enough data to define a second has dropped from 3 weeks to just a day and a half. Instead of helping you know when to wake up or go to bed, this type of atomic clock serves as the ultimate reference for calibrating other clocks and conducting high-precision physics experiments. It is critical for testing Einstein's theories, searching for dark matter, and understanding the universe at a deeper level. Atomic clocks use the vibrations of atoms, usually cesium or ions like aluminum, to measure time with extreme precision. Unlike regular clocks, they do not rely on mechanical parts, but instead track the consistent oscillations of atoms when they are hit with microwave or laser light. These clocks are the standard for defining a second and are used in GPS systems, telecommunications, and scientific research. Their accuracy allows scientists to test fundamental physics, like relativity, and even detect tiny changes in gravity or the Earth's rotation.
Physicists have discovered a new type of time crystal inside a diamond, which challenges our traditional understanding of time and motion. By bombarding a small diamond with lasers, researchers created what they believe is the first true time quasi-crystal, a state of matter where patterns in time are structured but do not repeat. Normal time crystals have particles that move back and forth in a repeating rhythm, like the repeating arrangement of atoms in everyday crystals such as diamonds or salt. However, this new time crystal is like a quasi-crystal, which has an organized structure that never exactly repeats, similar to certain patterns of tiles. To make this, scientists used special lasers on the diamond to create tiny imperfections. These imperfections allowed tiny particles called electrons to move in response to energy waves called microwaves. Because the microwaves had a rhythm that never repeated, the movement of the electrons also followed a rhythm that never repeated, creating the time quasi-crystal. This novel phase of matter has significant implications for quantum research and technology, potentially enabling long-term quantum memory, akin to quantum random access memory, though early stage. Creating a time quasi-crystal with a structured but non-repeating temporal pattern offers new insights into quantum mechanics and time crystals themselves, with potential future uses in metrology, precision timekeeping, quantum sensors, and quantum computing. Time crystals, theorized in 2012 and observed in 2016, are materials with self-sustaining, repeating temporal oscillations.